Hello and welcome to the Unit 2 podcast on Section 8.2, the formation of ionic bonds. I'm Mr. Sakaguchi,
And I'm Mr. Lin.
and let's start. So we talked about the formation of ions in the last podcast, and now we're going to talk about how ionic bonds form. Basically, the formation of oppositely charged ions results in ionic bonds because if they happen in proximity to each other, they'll come close together.
So they'll kind of click together like magnets of opposite charges. You got the positive charge, you got your negative charge, and then that's the attraction. That's
And we'll kind of illustrate more what's happening in a little bit.
Right.
There are a couple different kinds of ionic compounds. There are binary ionic compounds. These are ionic compounds composed of two different elements, whereas ternary ionic compounds contain three or more, and we'll talk about how that's actually possible.
Now the way these ions form is because the metals, they are positively charged because they lose their electrons. And if those electrons are lost, that means something else picks them up. And that goes to the nonmetals. Nonmetals will gain those electrons that were lost and therefore have a negative charge.
So electrons are always conserved in the sense that whatever the metals lose has to be gained by the nonmetals. And we can represent this loss and gain in a few different ways. So here's an illustration that kind of shows how sodium chloride becomes an ionic compound. So sodium has one valence electron, remember, and chlorine has 7. Now remember, in terms of ionization, to be like noble gases, chlorine wants to gain 1 and sodium wants to lose 1. So during this ionic bond process is also the formation of an ion as well, of ions. You have your electron from sodium being transferred to chlorine. The only reason why it's different colors so it indicates where the electron is. So you don't think that chlorine's magically getting an electron on its own. And then what ends up resulting is the formation of sodium ion and a chloride ion. So notice the difference between these products and these reactants in the formation of oppositely charged ions that if you add them up, would add up to 0. Also notice the change in name from chlorine to chloride. So IDE indicates that we have an ion, whereas chlorine indicates I have a neutral atom. And we'll talk more about how we get the name sodium chloride in later podcasts.
Yeah. So as you can see here in this slide, with calcium and chlorine, what's going on is the calcium's got 2 valence electrons that it wants to lose to get that noble gas electron config. But in this situation, calcium's going to want to lose 2, and chlorine only wants to grab 1 or gain 1. But what happens is the calcium will donate 1 electron to each chlorine. So that way calcium is still able to get its noble gas config that it wants to be stable, and chlorine each gets 1 extra electron to get the noble gas config that it wants, resulting in calcium losing those 2 electrons, having a positive 2 charge, and the chlorines wind up each gaining an electron and getting a negative charge each. Notice if you added up all the charges, again, equals 0.
And one thing to note is that as we're theoretically forming these compounds, we presumably have enough of the metal and the nonmetal to add as many as we need in order for this situation to actually happen. Now in the previous example, the ratio of positive to negative ion to add up to 0 was a 1-to-1 ratio. In other words, 1 sodium for every 1 chloride ion. In this example, notice how it's a 1-to-2 ratio. So for 1 calcium, there are 2 chloride ions. And then there's a way to indicate that in the formula as well, which we'll talk about later. Properties of ionic compounds: they form brittle solid crystals. A lattice just means that it's a regularly repeating structure, which will sometimes result in a translation of that lattice into a repeating 3-dimensional shape. These generally, all ionic compounds are called salts, so salt isn't necessarily just the stuff you put on your fries.
Right, and a result of this crystal lattice shape, because it's highly organized and structured, it gives you the high melting point that is typical of ionic compounds, and also a high boiling point.
Most ionic compounds dissolve in water or dissociate into ions, and we'll talk about what that is in a little bit.
And when they do dissolve, they form a solution called an electrolyte, which is able to conduct electricity.
And also in the molten state. So in other words, if we
Right.
melt down the ionic compound, it will also conduct electricity as well. In terms of electrolytes, not everything is an electrolyte. For instance, pure water by itself does not conduct electricity. If you've ever seen in movies, where the person throws like the toaster into the bathtub and the person gets electrocuted, it's not because of the water. It's because of the ions dissolved in the water.
Right.
The solid by itself in the solid state does not conduct electricity, but when it dissolves in water, the ions that it separates into allows electricity to conduct through the water and complete the circuit to light up this light bulb that you see in the figure here.
Right, because the conduction of electricity is really just the electrons getting passed on from one ion to another. And now that they're free from the highly rigid structure of a crystal lattice, and now they're freely moving when they're dissolved in water, that's why it conducts electricity. And we'll have labs to demonstrate this at a later point.
This figure here is just to illustrate what dissociation is. Now, if this is our salt, what ends up happening is water, it being polar in nature, is able to attract the positive cations and negative anions, and you have these little surroundings of ions by water molecules.
The thing to take note is that doesn't mean that ionic bonds are weak. They're actually some of the strongest there are. It's just that there are so many water molecules that are approaching the ionic solid that it kind of just nibbles off bits and pieces at a time, and that's what occurs during the dissociation.
Energy in the ionic bond. Usually during chemical reactions, energy is a factor we'll consider. Sometimes energy is absorbed during a reaction, which is another way of saying that is endothermic, or it could be exothermic if energy is released.
So when you're forming an ionic compound, that's always going to be considered an exothermic reaction. So it's always going to be releasing heat.
Basically, the compound is more stable than the ions would be if they were just alone by themselves. And what we find is the energy released during the bond formation would be the minimum amount of energy someone would need to put in order to separate these ions or break the bond.
So no energy is really gained or lost by, everything that's happening. Whatever you put in is exactly how much you can get out.
Right. So energy is conserved during chemical reactions and physical processes. Lattice energy. Lattice energy is energy specific for ionic compounds, and basically it's the energy necessary to separate a mole's worth of a compound. A mole doesn't mean anything to you yet, but it will in the future very soon. It's always a negative energy, and the reason why that is because you have to, remember it's an exothermic process, so this is energy leaving. So to break the bonds, we'd have to put the energy back in.
So the thing to understand is that the greater the lattice energy, the stronger the force of attraction, or the stronger the ionic bond. And this is related to the size of the ions. The smaller the ions are, the greater your lattice energy is going to be. So the smaller salts are actually going to have a stronger ionic bond strength.
And this is because there's less interference separating those electrons from the nuclei of the attracted ions. Also, the greater the charge, so something versus a +2 charge versus a +1 charge, will have a stronger lattice energy as well because there's a greater positive force.
Right.
And that can also be true on the negative side as well. And I think that's it. So until next time.